So good evening, students. So in the previous classes, we could complete the eigenvalue problem or discrete system. In the last class, we saw some special kind of eigenvalue problem that is called Patel. Any issue?
Sir, in the last example of the last class, on the slide number,
I will take up at that. Okay.
Okay, sir. Okay, sir.
So continuity will be lost. We'll take up at that. So I think we completed the semi-definite system in which we found that one of the eigenvalue can be 0 and the corresponding eigenvector is rigid body mode. That means the whole generalized coordinate are having the same magnitude. So the body, even if it is flexible, it moves in a rigid body mode. It moves as a rigid body. Whatever the example we took, eigenvalue problem maybe up to 3 by 3 matrix, but if it is more, then it becomes complex, especially if we take the determinant of the characteristic equation. We'll find that the polynomial will be 4th degree polynomial, and finding that will be difficult. So only possibility is to solve them then by numerical, like some software or by some numerical method. In subsequent chapters, we'll see those various methods. But today I will cover some very elementary approximate method, which is useful for finding mainly the fundamental natural frequency of the system. Because what happens in the real system, the fundamental frequency or the lowest natural frequency is the most dangerous because it may get into the resonance condition. That means the excitation frequency of the system, any external force which is coming to the system, it is likely that the first natural frequency may coincide with that because that is very low in magnitude. So often this method, which I'll be explaining, is useful for getting some rough estimate of the eigenvalue or the natural frequency of the system. So, but in the subsequent classes, we will see in more detail these methods, and even we can able to find out natural frequency for larger system by some approximate method. So I will take up that two particular concepts I will introduce today, and then I will take up some example. So one of them is this enclosure theorem. So this enclosure theorem, with this theorem, we can able to find out what is the minimum and maximum range of the eigenvalue of any discrete system. We will extend this theorem for continuous system also, but till now we have not covered the continuous system. So once we cover the continuous system, then we'll take up for continuous system. But today I'll be mainly focusing on the discrete system. That means having n degree of freedom system. So eigenvalue problem we have been writing If you remember, we had the differential equation, and then with something like assuming the solution in the separation of the time and the amplitude, we reduce the equation of motion into eigenvalue problem. And this is the eigenvalue problem, general eigenvalue problem, in which Ku is the displacement of the system. Omega square is the natural frequency, and if I write omega square as a lambda, then this is eigenvalue mass matrix, and the U is the displacement vector. So this is the standard eigenvalue problem which we solved in the previous two classes by taking the determinant of this to get the polynomial and other things. Okay, so but here we'll not solve this using that particular procedure, but by some approximation, by some guess, by guessing the displacement, and then we'll try to find out the range of the eigenvalue. So I'm defining the multiplication of the k with the u is v, and I'm defining mass into u as w. So this equation will become v is equal to lambda w. If I define like this, so this particular equation will simplify to v is equal to lambda w, where v is nothing but k into u and w is nothing but m into u. Now I'm defining a ratio, because if you see the v, what is the size of the v? V is a vector of size n into 1. Similarly, w is a vector of size n into 1, because we had the mass matrix and the stiffness matrix of n by n size. So we expect this v and w will be n by n vector. So we'll be having n component in the v and n component in the w. So if I take, let us say, jth component or the jth row of this v vector and jth row of the w vector component, and make a ratio of that vj by wj. So I'm defining that ratio as lambda j star. So lambda is eigenvalue, but here just to distinguish that they are different, I'm representing as a star. So this particular ratio, how many these ratios will be there? Because j we can take 1 to n, because we have n components, so we can take v1 by w1, so that will be nothing but the lambda 1 star. Then for second and third, like that. So we'll get n such ratios using this. Now these ratios is having some meaning. So the U vector, the K matrix generally we know from the formulation. Mass matrix also we know from the formulation. The U vector, which we don't know in this, we'll assume these U value. I will explain how we'll be using assuming this. So here U is a arbitrary vector which we are assuming with all its elements different than 0. So generally, when we choose the U vector, the element of that should not be 0, and it can take any other value. And so once we have this non-zero value, we will find that we'll get n number of such ratios, and among those ratio, obviously one will be minimum and the other will be maximum. Among all them, we will find out which is the minimum and which is the maximum. So minimum will represent as lambda me, and maximum ratio which we are getting from this. So among n, one will be minimum and another will be maximum. So we are defining the minimum and the maximum out of this. Others we are not interested. We are interested in the range. What is the minimum value of the ratio and the minimum value of the ratio, minimum and maximum. So according to this enclosure theorem, it states that if all the ratios are positive, whatever the ratio we are getting, if they are positive, then there at least one eigenvalue of the system will be enclosed by this particular range. So this is the statement. So whatever the ratio we got is having some minimum and maximum. We are ensuring that these ratios are not negative, or that if we are getting negative, then we need to choose different u. So u should be chosen such that it should not be 0. Also, the ratio which we are getting after multiplication of this should be positive. Then one of the eigenvalue will be within this range of the ratio. So is giving some idea about the eigenvalue within this two range. And often it is helpful for finding the, at least we can able to be sure that, because this eigenvalue is nothing but the, if we natural frequency is related with the natural frequency, if we take the square root of this, obviously we'll get the natural frequency is falling within this range. And negative, why it is not, it should not be there, because we need to take the square root. So if it is negative, these ratios are negative, then we'll be having the complex number that is not feasible. So this is the enclosure theorem, a very simple theorem. So let us see this through one example. So we have the K matrix, okay, from whatever the, because now you are familiar with the system, and from that you can able to obtain the equation of motion. So let us say you obtain the equation of motion, and the equation of, from that the stiffness matrix is this, and the mass matrix is this, where ID and other things are defined. So we are interested at present, let us say, the number. So the u vector which I was talking about here in the previous slide, this u vector, we are assuming something like this. So something like 2, 3, 2, arbitrary we have chosen. We ensure that none of them are 0. So this now will substitute in the definition of the V. So V, how we defined, that was the multiplication of the stiffness matrix into the U vector, which we have assumed. So stiffness matrix is given to us, U vector we are choosing it. If we multiply this, we'll get a vector of size n into 1, that is 3 into 1. So if we multiply this, we'll get V vector like this. Similarly, W vector is defined with respect to the mass into the same vector which we have chosen. So if we multiply these two, we'll get another vector. Okay, so we have 3 elements in this and 3 elements in this. Now what we'll do, we'll take the ratio of these. So that means the V1 divided by W1 is one ratio. V2 divided by W2 another ratio. Similarly, V3 divided by V or W4 or W3, this is another. So we'll get 3 ratio from this. So that is shown in the next slide. So this is the first ratio. You can see how we got the V and W in the previous slide. So V1 is 1 GL by L, and W1 is 2 into ID. So this is fine. You can see 1 by 2, 1 by 2. So ratio is 0.5. Similarly for V2 by W2, 2 by 3, 2 by 3, 2 by 3, so 0.667. This remains common. And this ratio is lambda 2 star, which is defined as the natural frequency square. So, and then the third ratio, that is 3 by 4. 3 by 4, and I think this factor should be common here. So I am writing at the end. So 3 by 4 is 0.75, and this remains the same. So among this, you can see this is the lowest one, 0.5, and this is the highest. Not necessarily it should be in this order. We can have this also lower depending upon how we are choosing the U. So, but for this particular case, this is the minimum 0.5, this, and this is the maximum. So this is the minimum, and this is the maximum. So we got the range of the, if we take the square root of this, we get the range of this natural frequency, which one of the natural frequency will be falling within this range. So it will enclose between these two, it will enclose one of the eigenvalue, and you can see that this is the minimum value, this is the maximum value, and as we know, using the conventional procedure of eigenvalue problem, we can find the eigenvalue of this. So if we find that, I think in the book there is example 4.3 in which this has been solved using conventional eigenvalue problem, and the lowest natural frequency of that was, or the square of the natural frequency was this 0.6594. So you can see whatever the range we got, 0.5 to 0.75, it is enclosing that particular natural frequency. Now, why it includes the lowest natural frequency? It depends upon the choice of the U. So if you go back again to the U, U is all positive. We have chosen all the positive. So generally, we have seen that the fundamental frequency are having the eigenvector, they're all the positive values, because all the generalized coordinates are having synchronous motion. They all are having positive displacement simultaneously, and again, when they are going to a negative, they are going simultaneously. So the choice of this is through once you have some experience, then you can able to see what this U I should choose, so that I can be able to find out the a particular natural frequency. So like when I took all positive, then I'm able to enclose the first natural frequency. Now let us see. So here, whatever the range was there, that was slightly wider, 0.5 to 0.75. If we, whatever the U we have chosen, if we fine tune that value, then this range may become more narrow. So this is the thing. This also arbitrary. We are changing 2 to 2.4 and 3 to 3.2. Earlier we took 2, 3, and 2. Now I have just, so 0.4 and 0.2 I added just to see how the range of this which we got, whether it is getting narrowed or not. So using previous calculations, we can able to obtain by multiplying this U with stiffness matrix. So we will get this. Then the W we can able to obtain by multiplying with the mass matrix, this U. So we'll get this. Now we can again we can find out this is the ratios. So 1/6 divided by 2.4, that will give this. 2 divided by 3.33, this will give this. Then 2.8 divided by 4, the third. Now if you see this we did not disturb anything, so it remains same. Or it got narrowed. Yeah, I think because of this they got affected. So this got narrowed. The highest value got narrowed from 0.75 to 0.7, and the lowest value, which was 0.5, now it has become 0.667. So this is the lowest. Sorry, this is the lowest. Okay, now this is the lowest. So this is the lowest and this is the highest. So okay, so now you can see the range in which we enclosed the first natural frequency got narrowed. So that means we could able to predict the frequency more closely as compared to the previous one. But this choice is all arbitrary. You need to try this value, that value, and then up to the satisfaction of the range you want to enclose, you need to try out, and then you need then you can stop at that particular time. Okay, so this regarding the first natural frequency we enclosed using taking the eigenvector like this. So here what we are doing, directly we are choosing the eigenvector without solving the eigenvalue problem. We are getting the some approximate range of the natural frequency. Next, the second case. If we take second case, let us say -2. Instead of 2, -2, 3, 2. So in this, what is happening? We are assuming that the second, the third, and the second masses are having similar direction of motion. That means, but the first is having opposite to that. So this kind of trend we have found usually in the second natural frequency, in which one of the mass is having opposite motion as compared to other. So if we use this instead of the previous u, and we obtain the v value, w value, then we'll find that we'll enclose the second natural frequency. This is actually the solution I have given here, which is example 4.3 from the textbook. So when we use all positive eigenvector, we enclose this. Now, if I take one of the extreme one is negative, in fact, this is eigenvector for first natural frequency, second natural frequency, third natural frequency. This has been obtained using the conventional eigenvalue problem, in which you take the determinant and solve the polynomial and then go for the eigenvalue calculation as we have done in the previous classes. So this is the lowest frequency, second, third, and corresponding to this lowest frequency, this is the eigenvector. You can see all are positive. Corresponding to this is the eigenvector. You can see one of the end was negative, because we can able to scale it if we multiply all by -1, or so it depends. Okay, so we can always able to scale it. If you multiply by -1, this minus minus, this will become plus. So here we have taken similar to that one, and we have taken negative and 3. So if you do this, I am leaving this to you. So you'll find that with this, you'll enclose this particular natural frequency, which is the exact natural frequency from conventional eigenvalue problem. This case, the third case, if you see the eigenvector of this third natural frequency, the middle one is having opposite motion as compared to the other two. So similar trend I would use. Values may not match, but the trend, like these two are having similar motion as compared to this. So this will enclose the third natural frequency. So this two calculation, because this is a simple calculation of the multiplying the this kind of matrices and getting the ratio. And once you got 3 ratio, you'll find that from this it will enclose this. And if you want to fine tune, maybe you can play with this. Either you can take this negative, this positive, or some small changes you can able to do, and you'll find that you can able to more closely you can able to enclose this. Similarly, you can try out this. Okay, so second and third, I am leaving it to you. Also, what we can do, this is the exact eigenvectors. And if you use this in this particular problem, obviously you'll get the exact natural frequencies, because these are exact eigenvector. So if you substitute in this enclosure theorem, you'll get the minimum and maximum same, equal to the respective natural frequency. From here, you'll get the same ratio for all of them. All three will be having same lambda 1, lambda 2, lambda 3. All three will be having same ratio. Similarly, from this, all three will be having this ratio. So this is the enclosure theorem. And now I'm giving a small Matlab script, so that this you can able to play with. You can able to, so like earlier we have used this script to obtain the natural frequency using the conventional eigenvalue problem. So this is the K matrix. I have defined this 3 by 3 matrix. This is the mass matrix, 3 by 3 matrix. This is the E matrix for finding the eigenvalue. And then this is the eigenvalue command in which we use the D matrix here to find the eigenvalue and eigenvector. So this Q gives the eigenvector. So here the way it has been defined, we need to take the inverse of that and then take the square root. So this will give the natural frequency. So from here we can get the exact natural frequency as we have got here. And then the eigenvector P, we can able to normalize here, normalize with respect to the first one. So this will give the, so this we have done in the previous class already. So now using the enclosure theorem, what we need to do, let us say case 1, or we assume the U as 2, 3, and 2. So this is representing the transport. That means this is a column vector U. So to get V, just we need to multiply the K matrix with the U. And to get W, we need to multiply the mass matrix with U. So we got the V and W. Now we need to take the ratio because this is 3 by 3 size vector. So we need to take the ratio of individual components like V1 by W1 like that. So this is the command to divide the two vector having individual component backslash dot. So this will give us V1 W1, V2 by W2, V3 by W3, all three lambda it will give. So this lambda will be 3 by 3, 3 into 1 vector. We can able to find out the minimum of this by this command and maximum of this from this command. So directly we can able to get the minimum and maximum lambda as we obtain here, minimum and maximum directly we can get here. So that will enclose one of the natural frequency, and as so this is the same which I assume, so you can able to get the same answer as we have got earlier. Now the other two, V1, as I said, if -2 is there, 3 and 2 is there, so same procedure can be followed. I think this should be, if we are saying V1, then this will be correspondingly this, and we can define this as so that, yeah, similarly this we can define. So this is the second case. Third case, similarly we can able to do by defining this. So this we can define as 2. This I think you can able to do. I'm just yeah. So you can able to get from this directly, but at least you do some by hand calculation so that you get some feel of this. But this can be used to play with other bigger number which I have given like this. So you can even feed U as this and check whether you are getting the exact natural frequency or not. This and this. So this was the enclosure theorem. There is another approximate quotient is there that is called Rayleigh's quotient, and we'll see this property of the Rayleigh's quotient now. So again, this is the eigenvalue problem. We have standard Ku lambda. Now, because this is eigenvalue problem, and if we have lambda r as one of the eigenvalue, and ur is corresponding eigenvector, so if we substitute this here in this eigenvalue problem, this will satisfy it because these are the solution of the eigenvalue problem. So if we substitute the solution, it should satisfy. So this has been written for the rth eigenvector and eigenvalue, but R can take 1 to n value. So we have R n number of such expressions. Now here I'm pre-multiplying both sides by a transpose of UR vector. Pre-multiplying means this side and this side, both sides I'm pre-multiplying. If I pre-multiply, then I can able to write the lambda R as, because this quantity I can bring it here. So this will be pre-multiplied UR in front of K UR, and this has been taken to the denominator. So UR transpose M this. So this particular ratio will be nothing but the eigen values. So if we are choosing these are eigenvectors, this will be the eigenvalue, where this can take R from 1 to n. But as we have chosen in the previous case, U something else. We are not chosen the same U. So if we are not choosing the same view, so let us say this particular thing. If you, let me delete this so that things are more. So we are not choosing the exact eigenvector. So if we are choosing other than the exact eigenvector, arbitrary vector, as we have chosen arbitrary in the previous example, then we'll get some ratio. Okay, that will be definitely not equal to this, but some ratio will get, and this ratio is called Rayleigh's quotient. This is called Rayleigh's quotient, and we'll see the property of this Rayleigh's quotient. So the Rayleigh's quotient Ru is a scalar quantity, because if you see in the previous thing, K is n by n matrix, but is post multiplied by U. So this becomes n into 1, and this is 1 into n. So basically multiplication will give a scalar quantity. Similarly in the denominator also. So we'll get a value from this, and that is a value is Rayleigh's quotient. And if U vector which we have chosen, if it is coinciding with one of the eigenvector, then the Rayleigh's quotient will give the corresponding eigenvalue. Okay. In the previous case, we have seen that any vector we can able to express in terms of the actual eigenvectors multiplied by the constant. This is the expansion theorem which we discussed earlier. So any arbitrary vector can be expressed in terms of the eigenvector multiplied by constant and summing up all the such quantity from 1 to n. And this can be written in a matrix form like this, because these are eigenvector. If we stack them in a matrix form, so this becomes the modal matrix, and C is the vector having C1, C2, C3 value. So just we have put this summation in a matrix form like this. So U, small u is equal to capital U, which is modal matrix, into constant C. If we take the transpose of this, obviously they will swap, and then transpose of that will be there. Here U is modal matrix, which is square matrix, and this C is having all the n components. And as usual, when we this model matrix, if we are normalized with respect to mass, then we get this multiplication is identity matrix, and with the stiffness we get the all the diagonal terms will be having the lambda, the values will be there. So if this was there's a mass normalized model matrix. So now going back to the previous Rayleigh's quotient, how we defined this, the Rayleigh's quotient definition. Now we want to substitute the U with this expansion theorem, capital U C, because here we are having transpose of that, so we'll use this. So U, when we put the U, capital U C, and then before that C transpose U transpose K. Similarly at the bottom we have substituted for U, so we got this. Now according to this mass normalization, the denominator, the U transpose and U will be identity matrix with this. So if this is the identity matrix, we can write that, and U transpose K into U will give a matrix having all diagonal terms as eigenvalues. Now, because this is identity matrix, this is C row vector, this C column vector. If you multiply them, you will get C1 square plus C2 square plus C3 square, like that. So that we can write as a summation form. In the top, because this is a diagonal term, so apart from the C1 square and C2 square, the lambda also will be coming. So it's something like C1 square lambda 1 plus C2 square lambda 2. So those terms will be there. So if you expand this, you will get in the summation form like this. So only difference is here lambda is coming, here lambda is not there. Now let us say whatever the U we have chosen, or the arbitrary vector, if it is very close to the rth eigenvector, if it is very close to rth eigenvector, then from this, if let us say it is exactly rth eigenvector, then what will happen? We should get this ratio equal to the rth eigenvalue. Or if I go back here, then things will be. So if my arbitrary U is rth eigenvector, then this ratio should be equal to the rth eigenvalue. If not, then some other value. So here we are saying ki, let us say U we have chosen is very close to UR. So that means it should be, it should have this. If you see here, the C's are what? C's are multiplied by the lambda. So here if you see C r square, lambda r square will be there. So to get this ratio equal to lambda r, the CR should be very big as compared to C1, C2, other values. So this is the thing we are saying, if U is close to UR, CR must be much larger than the remaining coefficients other than the R. So that means CI by CR, because CI is other values, are very small as compared to CR. So we are equating that to a small quantity epsilon I, which is very less than 1, because CR is dominating, because whatever the U we have chosen is very close to UR. So we have defined this. Now we are writing that particular previous expression. Sorry, this expression again here. But only thing, now I'm dividing numerator and denominator by 1 by CR square. 1 by CR square. Here I'm divided, here also I divided. Now if you see, if I expand this such that I take out from the summation the rth term, remaining term I am keeping in the summation. I've just taken out the rth term. Here also I have taken the rth term outside, remaining n minus 1 terms are here. Now if I apply this CR inside, so this will become lambda r, and because CR is not there in the summation, so it can go into the summation. So Ci square by CR square will be nothing but the lambda I square according to this definition. So this Ci square by lambda I have written as epsilon I square lambda I. Similarly, in the denominator, this will become 1 and this will become epsilon I square. Now, if you see, this is a small term because lambda epsilon I is small, and then square of that will be further small, and this is also small. So if we ignore this two terms, then this ratio will become lambda r. So Ru will be equal to lambda r when our u is very close to ur. So this is the higher order term. So lambda r, this Rayleigh's quotient will be equal to lambda r. Now, let us say if I'm choosing r is equal to 1. R is equal to 1. So because I can choose r any value, so I'm choosing r is equal to 1. So Rayleigh's quotient can be written as lambda 1, r is equal to 1 is there, plus here I will be from 2 to n because r is 1, so remaining m minus terms will be here. Similarly, in the denominator, 1 plus this remaining terms. Here there is no r, so this will be I is equal to 2 to n. Now this we can able to bring in the upper part by taking minus 1, and this can be approximated as using polynomial expansion. If we take the first term, so this minus will come inside, this will remain same. This is approximation, and if we multiply this, we'll get this terms, 4 terms will get, and the last term is basically you can see this epsilon square, and this is also epsilon square. So this is a and now lambda 1 is there, and I can club this two in this form. So the ratio become lambda 1 plus lambda I minus lambda 1 epsilon I square, like this, where I is from 1 or from 2 to n. So lambda I minus 1, this is very important. So lambda I is the second natural frequency, third natural frequency, like that. So always this particular quantity will be more than 0. Always it will be 0. Okay. So this is the Rayleigh's quotient for r is equal to 1. So that is nothing but lambda 1, which is the exact eigenvalue plus something because this quantity is always positive. So that means so whatever the value we'll get from here, the Rayleigh's quotient will be always it should be more than that. I think it should be always more than that. No? Rayleigh's quotient will be always, let me see, yeah, always more than that. Where is that? Or less than that, lambda 1. Okay. So Rayleigh's quotient is never less than the first eigenvalue, because first eigenvalue is lambda 1, and if there is error, this will add up to that. So that means always Rayleigh's quotient will be more than, or in the extreme case when the eigenvector is exactly the first eigenvector, then this will be equal to the lambda 1. So this is giving a some idea that this is giving a basically a bond to the lowest eigenvalue. Now coming to the, let us say in the second case, we are choosing r is equal to n. So earlier we chose r is equal to 1 here, r is equal to 1. Now I am choosing r is equal to n. So for that, what I need to do, n will be coming here, and then again the same process we can do. So I'll get lambda n minus lambda I. So here you'll see earlier we had lambda I minus lambda 1. Now here we have lambda n minus lambda I, other way around, and here negative. And lambda n is the highest natural frequency because we already talked that we'll arrange the natural frequency lowest at r is equal to 1 and highest at r is equal to n. So this is the highest natural frequency. And so lambda n is the highest natural frequency. The other ones will be less than that. So this quantity will be positive. So that means the Rayleigh's quotient, if we take r is equal to n, Rayleigh's quotient will be always less than the highest natural frequency of the system. Always it will be less than the always less than the highest natural frequency of the system. So you can see that the Rayleigh's quotient is giving, it will never be more than the highest natural frequency, and it will never be less than the lowest natural frequency. So something is giving a bound. What will be the range within that the natural frequency will fall, the others. So that is the concept of the Rayleigh's quotient, which is giving some fair idea what is the highest value the eigen vector can have and the lowest value it can have. So it's giving some kind of bound. Okay, there is this one specific case in between. In between, if we want to take, so I think I will take small question, then I will go for this because this is having some more concept. Or let me finish this, then I will take up the question because, yeah. So here, the last one is very specific case in which, let us say the choice of the vector u is such that it is not containing the first s minus 1 eigenvector. Is containing only the eigenvector from s to n. So in that particular case, according to the expansion theorem, if it is u is not containing the first eigenvector, first s minus 1 eigenvector, that means corresponding coefficients are 0. According to the expansion theorem, corresponding s minus 1 coefficients are 0. So if corresponding coefficients are 0, the Rayleigh's quotient will take value from I is equal to s to n, because the coefficients from 1 to s minus 1 are 0. So this will reduce to this particular form in which it will start from I is equal to s to n only. Now, because now it is having contribution from s to n, so if we again take the similar procedure as previous one, we'll see that this particular ratio will be always more than the lowest eigen value which is present in in this particular case. So here the lowest is I is equal to s among all the eigenvector present from s to n. So this ratio will be more than or equal to this, where s can be 2, 3, 4 up to n minus 1, because s is equal to 1 we already taken previously, and n also we have taken previously. So this will be within the from 2 to 1 less n minus 1. So if you want to find out the intermediate bonds, so this can be used, but for that the u have to be chosen accordingly, that should not contain the first s minus 1 eigenvectors in that. So For this, I think I'll take up some examples in the next class. But if you have questions till now or in the previous class, you can ask now. Yeah, questions, please. Patel. Maybe you can
Yes,
ask
sir.
question
Sir.
first in this lecture, okay? If you have
Okay, sir.
questions, yeah. Any other question? Okay, so Patel, you can ask.
Sir, in the last example, 4.3,
Yeah.
page 56. Sir, A matrix is, I think, different.
Okay, so you change it. I think some typo error maybe there.
Sir, but sir, we are getting 3 different columns. I am getting 3 different columns.
No, I'm saying if there is a typo error, you should intimate me through email. No, here I cannot sort out what is the column and no. So
Okay, sir.
the concept should be clear. If there is a typo error because I'm making this PPT's first time and so many errors may be there.
Okay,
So
sir.
so you indicate through email, I will correct it.
Okay, sir.
Because if I have typed which matrix? A matrix. This matrix.
Adjoint matrix, sir, for the
Okay.
lambda
Okay.
second value.
Okay. So I'll check it. I'll check
Okay,
it.
sir.
I'll check it. So this is the second, first case. No? Yeah. I'll check it. I'll check it.
Second case, sir. Second case. Lambda 2. Okay, sir.
This one, it's a second case. So what is there? So I need to 1, 3,
Yes,
first row, second column, first row, second column, -1. This should be minus first row, second column, -1, -1. This should be -1, you said, no?
yes, sir. So 8, 2, 8, 1, 2, and
Yeah.
those are becoming 0, 0.
Yeah. I'll check it. I'll check it. These are just
Okay, sir.
numbers. I'll check it. But this will come same. This will not change. So some error somewhere. I'll check this. Any other question from today's lecture? Okay, so in the next class, we'll start with the continuous system. In that, basically, very simple cases we can able to solve in the closed form because once the boundary conditions are complex, then the equations become very complex to solve. So very simple cases we'll take up, and then after this, I think again we need to go back to the more detailed approximate methods for discrete system as well as the continuous system. Okay, so I think tomorrow we have class at 5 o'clock. So we'll meet again.